Okay, 12.1a, we're going to take a look at sequences, which is something that we saw last year, but it's going to be a little bit more review for us. Okay, a sequence is an ordered list of numbers, so we have a set of numbers and they all come in a specific order or a sequence. We can talk about some arbitrary term somewhere out there, we call that the nth term. And any function where the domain, so the inputs, are a subset of the positive integers would be considered a sequence. So if you're just plugging in 1, 2, 3, 4, or maybe you're plugging in all the evens, some subset of the positive integers. And if you have a finite domain, that means you have a finite sequence, so the list comes to an end. And we're going to be mostly concerned with infinite sequences, so that list goes on and on and on. We can define a sequence explicitly, which means we have a formula that allows you to find each individual term. So for example, here we could find whichever term we want. If we want the 10th term, just plug in n equals 10. If we want the 100th term, plug in n equals 100. And we can find the value of the 100th term. We can define a function recursively, which means we find each term based off of the previous term or maybe the previous two terms. So we could have something like this. We know our first term is 4. The nth term is the n minus first term, which means the term that comes before it, plus 2. So if we want the second term, we would take b sub 1 plus 2. b sub 1 is 4, so that'd give you 6. b sub 3 would be 8, and so on. If we wanted to find the 100th term based off of a recursive formula, it's going to take us a lot longer. We'd have to go through this 100 times to get to that term. And we have a special type of sequence called an arithmetic sequence, which has a common difference. So the difference here, or the amount that we add to get from one term to the next, is 3. And here, natural logs, keep in mind that if you take the difference of natural logs, that's the natural log of the fraction. And so all of these have a common difference of natural log of 3. And we can define these recursively, as so, or explicitly, like this. And just keep in mind that repeated addition is shown as multiplication, so it makes sense how we come up with this explicit formula that we add that common difference over and over and over again, n minus 1 times, so d times n minus 1. A geometric sequence has a common ratio, meaning you multiply by the same thing each time. In this case, we multiply by -2, we say r equals -2. Multiply by 10, r equals 10. And we can define these recursively by taking each term multiplying by the common ratio, or explicitly, we have the first term times the common ratio to the power of n minus 1 because we've multiplied by r n minus 1 times. And so let's just take a look at an example here. We have a geometric sequence. We know that the second term is 6, the fifth term is -48. We want to find an explicit rule for the nth term. So we know that a sub n is a sub 1 times r to the power of n minus 1. So a sub 2 would be a sub 1 times r to the power of 1, and we know that that's 6. A sub 5 would be a sub 1 times r to the power of 4. We know that that's -48. And if we divide these two functions, a sub 5 over a sub 2, we can see that a sub 1 cancels out. We get -48 over 4, and r to the fourth over r is r cubed. So r cubed is -8, which means r must be -2. So we've figured out from this our common ratio. And again, we know that a sub 2 equals a sub 1 times r to the power of 2 minus 1. Well, we know that r is -2. We know that a sub 2 is 6, so a sub 1 must be -3. So now putting this all together, we have an explicit formula for this geometric sequence. And we can graph these on our calculators. Might be interesting just to see how that works. There may be times when we need this, but it's not going to be one of those big concepts we need to be able to do. But you can find the sequence graphing. You can graph the sequence using n. And here's what our sequence would look like. You can change the window. So we had on the previous one an explicit sequence. Now we're going to look at a recursive sequence, and our calculator can graph recursive sequences as well. So we know the first term, we know the second term. We're looking at the Fibonacci sequence, which is the sum of the previous two terms. And so we can type it in just like this right here. So we're referencing back to u sub 1. So the n minus 2 term and the n minus 1 term, you add them together. We have to give those initial terms. And the calculator will graph the Fibonacci sequence. We can view this as a table. And here's the stuff that will start looking familiar from last year. We can determine convergence of the sequence. A sequence converges if it's approaching some finite number as n approaches infinity. So we take the limit as n approaches infinity. Now here's one way to evaluate this limit. We can separate it and evaluate each one independently, and we end up with 2. You could also just use the terms with higher degree, and we know that those are going to be more powerful, so the minus 1 really doesn't matter. 2n over n simplifies to 2, and you could get to that limit value of 2 that way. It's up to you. I'm okay with us going with a little more informal approach. And we have a theorem here to allow us to determine the convergence of sequences. If the terms have some positive and some negative, you can just take the limit of the absolute value, and if the limit of the absolute value of the terms approaches 0, then the sequence still converges to 0.